All right, next I'd like to take a look in more detail at molecules. And so we've done some Schrödinger equation solutions for single atoms. We've applied this to the general case of a molecule, but a very simple kind of a molecule that turns out to be a covalent molecule. The H2 molecule is covalent. But here I'd like to look more specifically at the different types of matter and how they relate to different kinds of molecules. And so we have two principal types that I'll be discussing here, ionic and covalent. In an ionic bond, the atoms have unequal strengths on the orbiting electrons. In such a way that essentially one of the electrons, one of the outermost electrons, is stolen from one of the atoms and then delivered to the other. Okay, and so we can think of ionic then, if we want to make this a simple, easy thing to remember, as being due to electron stealing. Whereas in a covalent bond, we have electron sharing. Which means that the two atoms which are forming together, or it could be more than two atoms if you have a polyatomic molecule, have relatively equal amounts of pull on the orbiting electron. Okay, and so an example then of ionic, I'll start with ionic. Sodium chloride, NaCl. Now, for NaCl to work, the sodium atom must have a weaker pull on its outermost electron. And so that will give it a net positive charge, whereas the chlorine atom will have a stronger pull and basically steal the sodium's electron. And that will give the ionic crystal a dipole moment, because now we have a separation between positive and negative. And so then this can line up with a bunch of other positives and negatives so that you can end up with a crystal that looks something like this. Positive, negative, positive, negative, positive, negative. And then that can extend on this way too. It can go negative, positive, and then negative, positive. And so it can build up its structure into a 3D lattice. Okay, but to see whether or not this kind of a structure is stable in itself, we have to consider that we have attractive forces between adjacent atoms, say with respect to this central sodium atom here, but we have repulsive forces due to the ones that are a little farther away, and we have attractive forces due to the ones that are even farther away, but it's an infinite series of attractive and repulsive forces. So we have to be careful before we say that this is stable. Well, let's check. How can we check this? Well, we can look at the general expression for the potential energy for two spherical charges. And so that potential energy expression looks like 1 over 4 pi epsilon naught times Q1 times Q2 over R. Okay, so here's our charge Q1, here's our charge Q2, and then here's our distance R. Okay, so in this problem, Q1 and Q2 will be essentially the same, and that will equal the charge on an electron, because the electron is being taken from one and added to the other one. Okay, and so the charges here are going to be, one is going to be plus E, one's going to be minus E. So this is going to look like minus 1 over 4 pi epsilon naught times E squared over R. Okay, and so that's going to be the general expression for potential energy. But we have an infinite series of these. Okay, because this one and that one will be negative, but this one will be positive. And so for this thing to be stable, U has to be less than 0. Because that's the only way that we can get an attractive force, is to have a negative value for the potential energy. Okay, and so that is something that we showed in Physics 208b. And so the potential energy then, as a function of R, becomes less and less negative until it finally reaches 0 at infinity. So the biggest that the potential energy can get in this kind of expression is 0, but you can still have a difference in potential energy that's positive as you move one object farther away from another. If one's positive, one's negative. It's just like lifting an object against gravity. You have to lift it against the force of attraction, and that gives you potential energy. So you can have a change in potential energy while having the actual value of the potential energy still always being negative. But if this number is positive, then that means that they repel. Okay, so our check then to see whether our ionic crystal is stable or not is whether it's negative. If we can show that it's negative, then we can show that it'll be stable. So let's see how that would work. So here we'll start in the center, and let's just do this along a line. So this one is positive, next one is negative, the next one is positive, the next one is negative. So this distance here would be, let's call it A. Then this distance would be 2A. This distance here would be 3A. And U total, from the interaction of all of the rest of these ions on the central ion, would be equal to, well, this would be U1, so that would be equal to minus 1 over 4 pi epsilon naught times E squared over A. Then U2, that would be plus 1 over 4 pi epsilon naught E squared over 2A. And for the next one will be attractive again, so that'll be minus E squared over 4 pi epsilon naught 1 over 4 pi epsilon naught times E squared over 3A plus, and then we just keep going with this, 1 over 4 pi epsilon naught E squared over 4A. So this is an alternating series of positives and negatives. But we can turn this in, even though this is an infinite series, this converges. This is a convergent infinite series, so it doesn't add up to infinity. Even though there's an infinite number of terms in an infinitely long crystal. Okay, so our common factor then is going to be minus 1 over 4 pi epsilon naught E squared over A. And then we're going to multiply that by, well, this first term is going to be 1. The second term is going to be minus 1/2, okay, because I've already pulled out a negative here. So then that means that if I pulled out the negative here, then this first term will be positive, but the second one will be negative. The third one will be positive, that's 1/3. Fourth one will be negative, that's 1/4. The next one will be positive, 1/5 minus 1/6, and then this goes all the way out to infinity. But this is a convergent infinite series, and this converges to the natural log of 2. Because the log of 1 plus x is equal to x minus x squared over 2 plus x cubed over 3 minus x to the 4th over 4 plus x to the 5th over 5. And so in this case, x is 1. Okay, so the natural log of 2 then is going to be 1 minus 1/2 plus 1/3 minus 1/4 plus 1/5 minus dot dot dot. So that's the natural log of 2. Okay, so U total is equal to minus 2 log 2. Why 2? Because if this is a one-dimensional crystal, you also have the same contribution for all these other ones going out to negative infinity as well. Okay, so this is just along a line. This is a 1D crystal, has a U total that's minus 2 log cubed, minus 2 log 2 times 1 over 4 pi epsilon naught e squared over a. And so that's negative. And so that shows us then that a one-dimensional crystal is stable. If a one-dimensional crystal is stable, then a three-dimensional crystal is just a combination of that also acting in this direction as well as in that direction, as well as all the diagonal directions that you could work on. And so your alpha value is going to be a little different for each one. But that is the kind of thing that they do in more advanced analysis, is figure out what that value of alpha would be if you carried out that same kind of procedure for a three-dimensional crystal. Okay, so this shows us then that it will spontaneously tend to go into this state, provided that there's enough energy to tear off the electron. So there's actually 2 steps here. This proves that the crystal structure itself is stable, but it already has to be an ion before this can happen. So first you have to make the ion. So here are our steps in making an ionic crystal. And this is how you calculate the energy that's contained within an ionic crystal. Step 1, you have to take the electron off of one of the atoms and add it to the other one. Now this is going to be a positive value because it takes more energy to ionize an electron. Let's say that we're taking this off of sodium and adding it to chlorine. That'll make this side positive, that'll make that side negative. So you have to tear that electron off. You have to bring that ion all the way to infinity, and then you have to drop it back in to this chlorine atom. You get a little bit of energy back there, but not as much as you had to spend to ionize it from sodium. And so this costs you energy, and so this is going to be a positive energy. Then step 2, you combine your ions together into an ionic crystal. And so that releases energy, or negative energy. Because it doesn't take energy to make this happen. This automatically gives off energy. And so this term tends to be larger than that term. And so that means that this will spontaneously occur. And this is why table salt will tend to form from a solution that contains sodium and chlorine. They'll dissolve, but then if you evaporate off the water, they'll form back into an ionic crystal. And so this is the case at the bottom of the Mediterranean. Mediterranean Sea evaporated something like 5 million years ago, 5 million. And so now, then water eventually flowed back in, but a whole bunch of salt built up on the bottom of the Mediterranean Sea. And so it's like meters deep now in salt. And so this salt became an ionic crystal that formed spontaneously because it took less energy to move the electron from here to there than you gain by allowing the whole system to jump into this lower energy state in which it could form an ionic crystal. So this is the way then that you can determine the energy of an ionic crystal is by going through these two steps mathematically, figuring out the ionization energy for sodium, then dropping it back in to this elevated energy state for the chlorine atom to fill its octet structure, and then to just allow the ions to move together. Okay, so that takes care of an ionic crystal. Now we'll talk a little more about purely covalent crystals in a little while. What I wanted to do next is take a look at the vibrational and rotational states for a molecule. Now, a molecule that's often used for this is carbon monoxide. And carbon monoxide is CO, and it is useful because it is a simpler kind of molecule than, for example, CO2. It's linear. Also, the oxygen molecule, it's partially ionic because the oxygen molecule has a stronger pull on the carbon's electrons. And so because of that, there's a dipole moment. It's a slightly polar molecule. Now, if something is purely covalent, there's equal sharing of the electron, and that means there's no dipole moment, meaning there's no polarity at all. There's no positive end, no negative end. And so in the case then of carbon monoxide, there is, but that's useful to us because it can then interact with electromagnetic radiation, but only if it's got a charge. Only charges can interact with electromagnetic waves. This can result in the absorption or the emission of photons from the object. And so this is important to us because we want to know what's going on with various molecular components in the atmosphere. For example, if we're worried about global warming, we would want to know how much the photons in the atmosphere could interact with the molecules that are in the atmosphere. And that then can give us a better feeling for what might be causing global climate change. And so these things are important, but we'll start out with a fairly simple example, which is carbon monoxide, not one that is nonlinear, because those are much more difficult to deal with. All right, so there are two different kinds of states that the carbon monoxide molecule can find itself in. One is a rotational state, in which there's a tendency to make it want to rotate round and round like this, and there is a vibrational state. And a vibrational state is one in which you can imagine the forces of attraction between the two objects to be like a spring that allows for it to vibrate back and forth. But in quantum mechanics, these rotational states and these vibrational states are quantized, which means that they come in discrete amounts. And so you don't just have something vibrating like this and then slowly changing to where it's vibrating like this, but rather it's either doing this, or it's doing that, or it's doing this, but nothing in between. And similarly with the rotation states, it's kind of surprising that if you've got a molecule like this that's rotating, it can either be not rotating at all, or when it absorbs its first photon that allows for a rotational state, it's already going something like 1 billion cycles a second, and nothing in between. So it can't go 20 cycles a second, but it can go 1 billion cycles a second, or then there are certain mathematical relationships where it can jump discontinuously to other values of the rotation, but nothing in between. And so that's kind of crazy, but it's what quantum mechanics tells us. And so what I want to do first is take a look at the rotational states. Now, how do we do those? Well, in a rotational state, we can say that the angular momentum, L, is we can think of it as I omega, but in accordance with our solutions to the Schrodinger equation, we can write this as the square root of little l times little l plus 1 times h bar. So we've already seen that this sort of thing works for an object that is rotating in the solution that we got for the angular momentum for the hydrogen atom. And so that still works here for molecules. But the total energy is equal to 1/2 I omega squared. But we also know that L is equal to I omega. Okay? And so we could rewrite this then as I squared omega squared divided by 2I. So that's the same thing as 1/2 I omega squared. But remember before when we did this for kinetic energy, we could either write kinetic energy as 1/2 mv squared, or we could write it as p squared over 2m. And so here, we're going to write this, instead of writing it as 1/2 I omega squared, we're going to use the more fundamental quantity of angular momentum, as write this as L squared over 2I. Because L already has this quantum mechanical formulation associated with it. And then what's the I? Well, the I, measured from the center of mass, say if this is the carbon atom, this is the oxygen atom, this is going to be R1, this is going to be R2, and so we'd have I total would equal 1/2 M1 R1 squared plus, MR1 squared for point mass plus M2 R2 squared. Okay, where M1 would be, for example, here the mass of the carbon, M2 would be the mass of the oxygen, the R1 and R2 would be the distances from the center of mass for each. And so we assume that this object is rotating about its center of mass. But we also have, because of the condition for center of mass, we have M1 R1 equals M2 R2. So this is just the condition for locating that position correctly for the center of mass. This has to be the balance point. And the balance point is defined by this equation. This basically sets the torques equal if you pivoted about this point with some kind of something that would hold it steady at that point. So we can take this expression, plug it into that expression, and do a little bit of math, and what we end up with is M prime times big R squared, where big R is equal to what we call our bond length, and big R from this picture here is just R1 plus R2. So it's just the physical distance between the two molecules. And M prime is what we call our reduced mass, which is equal to, just very simply, the product of the two masses divided by the sum. So this problem, with the two atoms rotating about the center of mass, is equivalent to this problem mathematically. Where we have a single mass, M prime, rotating round and round a center here. Okay, so this problem is mathematically equivalent to that one, and is easier to work with mathematically. A lot easier to work with if we just have a single mass, but we just have to write it in terms of its reduced mass here. But then we're dealing with the bond length and not the distances from the center of mass to each atom, which is not as convenient for these kind of problems. Okay, so what we can do then is use this expression to get the moment of inertia of the carbon monoxide molecule. So let's do that next. Here we've got E is equal to L squared over 2I, but our moment of inertia for CO is going to be equal to mass of C times the mass of O divided by the mass of C plus the mass of O times R squared. And let's say that we know what that bond length is, and we know what the mass of the carbon and the oxygen are. For the carbon, the mass of the carbon is equal to 1.9 times 10 to the minus 26 kilograms. The mass of the oxygen is 2.66 times 10 to the minus 26 kilograms. And the bond length, R, is given to be equal to 1.13 angstroms. Or that's 1.13 times 10 to the minus 10 meters. Okay, so from that, we should be able to plug those values in for I and get an appropriate expression. But it will be a tiny, tiny number. Okay, so here, the 10 to the minus 26's cancel out in our reduced mass expression. Remember, this is just M prime times R squared, where R is our bond length. Okay, and so that's going to be just 1.9 times 2.66 divided by 1.9 plus 2.66, all multiplied by 1.3 times 10 to the minus 10 meters, quantity squared. And so that gives us, for the moment of inertia, I is equal to 1.46 times 10 to the minus 46. And so that's a pretty small number, but we're talking about just a little molecule here. That has units of kilogram meter squared. So that's our I value. And so once we have our I value, then we should be able to figure out the energy of the different excited states. Remember, the E of L states are equal to L squared over 2I. But L, angular momentum, is little l times L plus 1. It's the square root of that, remember? Square root of little l times L plus 1, h bar. So then that gets rid of the square root here, but then we have an h bar squared on the outside divided by 2I. Okay, and so that'll be L times L plus 1 times h bar squared. That's 6.63 times 10 to the minus 34 joule seconds squared divided by 2 pi squared times 2 times I. And then I is this value, 1.46 times 10 to the minus 46. And so here, let's find the lowest energy state. That's not equal to 0. Okay, and so that would be here when L is 1. If little l is 1, then 1 times 1 plus 1 is 2. So that'll give us a 2 in here. And so if we solve that then for the energy, that gives us 7.61 times 10 to the minus 23 joules. If we convert joules into electron volts, that gives us our answer as 4.76 times 10 to the minus 4 electron volts. So it's just a tiny fraction of an electron volt, just something like a 10,000th of the energy that is associated with 1 electron volt. And so this is something that tends to happen in the microwave part of the spectrum. Because microwave photons tend to have those kind of energies. Okay? And so if we want to then figure out from that what our rotational velocity is, then we can just set the total energy equal to 1/2 I omega squared. Set that equal to our minimum value here, which is 7.61 times 10 to the minus 23 joules. And so in this case, I'm not writing it as L squared over 2I, but 1/2 I omega squared. And so this is for L equals 1, which is our lowest vibrational energy state, or rotational, sorry. So we can then solve this for omega. That's going to be equal to, what, 2e divided by I square root, which is going to be square root of 2 times 7.61 times 10 to the minus 23 joules divided by I, which we still have over here, is 1.46 times 10 to the minus 46 kilogram meter squared. That gives us an astonishing value of 3.23 times 10 to the 11th radians per second. Now if we want to convert that into frequency, F then would be omega over 2 pi And so that would give us 5.14 times 10 to the 10th power hertz. Okay, and so what is that then? Well, this is something like 51 billion hertz. 51 billion hertz. So the molecule then is either not rotating, or when it absorbs its first photon, which would have to have this energy, just 4.76 times 10 to the minus 4 electron volts, it would shoot it up to 51 billion hertz. Okay? So that's how many turns per second it would go. That's how many complete cycles of rotation, 51 billion complete rotations per second would be our lowest value for the rotational energy state. So what would the next lowest one be? Well, the next lowest one would be when L equals 2. So if L is equal to 2 in this, then you'd have 2 times 2 plus 1 is 3. So instead of this being a 2, it would be a 6. Okay, and so that would be 3 times more than this. Okay, so your next energy would be 3 times more than that, or it would be something like here, 1.2 times 10 to the minus 3 electron volts. About 3 times this too. Okay, and so the energy levels go up, but they go up relatively slowly in increments of something like a 10,000th of an electron volt. Now again, photons that are in this frequency range tend to be in the microwave part of the electromagnetic spectrum. So what I've asked you to do in our lab for this week is take the molecular simulation for the carbon monoxide molecule and bombard it with all of the different forms of electromagnetic radiation that it allows you to do. And what you'll see is that in the microwave part of the spectrum, it'll rotate it. It'll make it rotate. But in the infrared part of the spectrum, it'll make it vibrate. Okay? And so that'll be higher energy that is associated with vibration than with rotation. So that's what I'd like to get to next. Let's now look at the vibrational energy states. What we just looked at here is rotation, now vibration. And of course, this can be done for any kind of molecule. It doesn't have to be the carbon monoxide molecule, but it just happens to be a good example. Now, for you to have a vibrational energy state, what you need to have is a potential energy function that goes negative, as we saw before with the ionic crystal. So it tends to drop down like this, and so up close, there's actually a little bit of a repulsive force due to the fact that the electrons don't want to get too close together. And so there's an exchange force there that is associated with that, because the two electrons that are in similar energy states are going to tend to repel because of the exchange force. Okay, so there's an exchange force repulsion. There's also electric repulsion. There's physical electron repulsion, but there's also the fact that they have to be an antisymmetric total wave function, and if the two electrons are in the same state, then that has an effective repulsion. And so that gives rise to a very positive value for you, which means that it's not going to want to be there, because positive values for you are not stable. Okay, but negative values are. And so down in here, the atom can find a point of stability. And so this is very much, though, like a simple harmonic oscillator potential, if we use what's called the parabolic approximation. So in this region that's nearby to the minimum, we can get solutions to the simple harmonic oscillator because of the parabolic approximation. So that means that you can be, and so what's this distance then? Well, this is u versus r. And so this distance here then is the distance between the two atoms basically. And so that's your bond length. That's your r. That's your bond length. So that's your distance. But it can vibrate back and forth about that to plus or minus that value. So if it goes to that value or to the negative of that value, then that just corresponds to different vibrational states that you can be in the simple harmonic oscillator potential. Assuming that the parabola fits the potential energy versus our plot pretty well at the bottom of this. And so in the parabolic approximation then, u is equal to 1/2 k times, in this case, well, we could call it x. But it's our bond length squared. Okay? And so this has a solution that we saw before for the simple harmonic oscillator, where the nth value for the energy is equal to n plus 1/2 times h bar omega, or n plus 1/2 Planck's constant times the frequency. Okay, and so what we need to do here then is to work this through is to find a natural vibrational state. So in this next example, say that we're told that carbon monoxide is dissolved in a solution and infrared radiation is absorbed. Now, infrared is higher energy than the microwave that we were looking at before. So the microwave will tend to stimulate carbon monoxide into rotational modes. You'll also see in the simulation that I set up for you for this week that when you do that for oxygen, it'll also, for water, it'll tend to also make water want to rotate. Okay, and so that's what makes a microwave oven work, is that you put food in a microwave oven that has water in it. Then the water molecules are also excited into their rotational states by the photons that are produced by the microwave oven. But you go to higher energies, and then it's the vibrational states that are absorbing. And so that's the kind of thing then that can turn this into a greenhouse problem. Because if it's infrared radiation that's absorbed, then that means that the natural energy of the oscillation can be excited, and that means that the atoms can, and the molecules can absorb that infrared radiation. And that's what puts a cap on the infrared and keeps the infrared from escaping from our atmosphere. Okay, so here infrared radiation is absorbed in a CO solution. So that means then that we know that infrared radiation is associated with some kind of a vibrational state. And I'll show that by actually calculating the energy of the vibrational state in a second. Okay, and so this radiation has a frequency of 6.42 times 10 to the 13th power. Now, microwave radiation is more like 10 to the 10th power for the frequency. So this is 1,000 times more when we get into infrared than what we have in a microwave oven in terms of the energy of the individual photons. Okay, and so from this information then, let's see if we can go ahead and figure out what the energy is for the absorbed photon. So we'll find the energy of the vibration first. So we can get that from the fact that delta E is equal to n plus 1/2 times h bar omega minus n h bar omega. And so that's just equal to h bar omega. So our difference in energy for a simple harmonic oscillator is just h bar omega, or Planck's constant times the frequency. And so every elevation in the energy state of a simple harmonic oscillator, as we saw before, is associated with an increment of energy that's equal to the energy of a photon. So that means that a photon can absorb this amount of energy and elevate the simple harmonic oscillator to its next highest energy state. So it's going like this, then it's elevated to, say, this state at the next highest value for n. And so that's what this frequency of a photon is doing. And that's also the frequency, because it's in tune with the simple harmonic oscillator, frequency of the photon has to equal the frequency of the simple harmonic oscillation. Okay, so all of that in mind then, we can go ahead and find, we'll find the energy first. So that's going to be equal to 6.63 times 10 to the minus 34 joule seconds divided by 2 pi for h bar, Planck's constant over 2 pi, times omega, that's 2 pi times the frequency, so the 2 pi's cancel here, and that gives us a frequency of 6.42 times 10 to the 13 hertz. So that gives us an energy then of 4.26 times 10 to the minus 20 joules, or that's equal to 0.266 eV. Okay, so now we're on the order not of 10,000ths of an eV, but more on the order of electron volts. And so back over here, we can see then that between each state of vibrational energy, we've got maybe 1,000 rotational states. And these rotational states have a difference in energy on the order of maybe 1/10,000th of an electron volt. But then interspersed are the vibrational states. Then we'd have a few more thousand of these rotational states, and then another vibrational state. And then a few more thousand, tens of thousands of rotational states, and then another vibrational state. And so it takes a lot of energy to get up to the point to where you can have your first vibrational state, but while that's happening, the microwave radiation can be causing the rotational speed to increase. But while that's happening, the vibrational state will only start to increase when you get to a certain critically larger value for the frequency. Okay, so given that all of this is going to work for us, then how do we find, say, the spring constant for the molecule? Okay. Well, the way that we can do that is, first of all, what we have is a molecule that's vibrating back and forth like this. And so both of these things are moving back and forth about a common center of mass. Okay, so while this is happening, it's also rotating. Okay, so as it rotates, the vibrational states go in and out like that. And so you've got the rotational states happening too. Okay? And so the part that's going in and out like that is the vibrational state, but while that's happening, the whole thing is rotating too. So it's a mess unless you separate it out into the vibrational part and treat that separately from the rotational part. Okay, and so you can do the same kind of analysis that we did before with the rotational state. And what we find in that situation is that omega is equal to the square root of k over m prime. Okay, so instead of it being the square root of k over m like it would be for a single mass, here we have two masses that are vibrating back and forth that are unconstrained other than that they are moving about a common center of mass. And so that center of mass stays in the same position while this is all happening. That m prime here is equal to our reduced mass from that previous discussion. So m prime is equal to m1 times m2 divided by m1 plus m2. Okay. And so this then is equivalent to a single mass, mass m prime, vibrating back and forth about the bond width. So this is r, but it's going back and forth about that value of r. So here, this is about some equilibrium position that's equal to r, but just moving back and forth with simple harmonic motion with the same value for the spring constant k. So in other words, using this expression, we can treat it as a single mass problem, even though it's two masses that are vibrating around a common center of mass. Okay, so once we've established that, basically the easiest way to remember this is, well, we just have to use reduced mass whenever we're dealing with this, and then we can use the same equations that we were using before. So if we do that here, we find that the spring constant, k, for this problem is equal to m prime omega squared, multiplying both sides, first squaring both sides, and then multiplying both sides through by m prime. And then m prime is going to be our reduced mass, which we had before as being, this is 1.9 times 2.66, and then the powers of 10 to the 27 cancel in numerator and denominator. m1 times m2 divided by m1 plus m2, 2.66 times omega squared. That's going to be 2 pi squared times the frequency squared. We had the frequency given before. Erased it, but the frequency was 6.42 times 10 to the 13th. Hertz quantity squared. And so we crunch out all these numbers, we get that it's equal to something like 1,800 value that I was getting before. Yeah. So it's 1.86 times, it's 1.86 times 10 to the 3. Newton per meter. So this spring constant then is something like 1,860 newtons per meter, which is somewhat comparable to the spring constant for the support springs on a car. Okay, but this is for a molecule. And so this explains, though, why the frequency is so large. You've got a very large restoring force because you've got a high spring constant. And so that large restoring force then gives rise to a huge frequency. Frequency on the order of 6.42 times 10 to the 13, that's 64.2 trillion hertz.